Good morning everyone. I just noticed that because I tried to put an emoji, the chat thing has brought up an emoji box at the bottom and I don't quite know how to get rid of it. So let's see if I can... Oh, I think I did it. There we go. Yeah, so loads of people turning up. Hello, good morning Jackson, good morning Freya. We've got Jack here as well, good morning. If you've just joined us... Oh, hello Lex. Yes, if you've just joined us and you haven't already seen the link, then I'm just going to post that into the chat thing now. If you could click that link and that way, oh, hello 𝗭𝘪𝘯𝘬𝘴. Yes, if you click that link, then that way you'll be able to interact live with us as we go through this. I'm using the quickfire quiz thing on Spiral so that when I ask questions, you either type your answer into that and it will bounce through to me and I can have a look at the answers. And that way people aren't just copying each other's answers, but also there's a certain amount of anonymity to the answers you're giving. So it doesn't matter if you make mistakes. You have to allow yourself to make mistakes. Today's session's all about quantum physics, a very brief 1 hour introduction to quantum physics, but it's a good topic. Hello, Tilly, good morning. Yes, it's a good topic, and it's a topic that's accessible to GCSE students as well as A-level students. It's a nice primer for GCSE students. That should give a bit of an explanation of some of the things that you've learnt about potentially in GCSE chemistry, but also in GCSE physics, we have to learn about the Bohr model of the atom. We're going to have a brief look today at the next step beyond that, which will help us understand that Bohr model of the atom. But for A-level students, it's going to be a very, very useful session indeed, with plenty of practice, looking at some of the most basic principles in quantum physics. And next week's session's about quantum phenomena, where we dig a little bit deeper into some of those effects that come out of quantum physics. But let's get on with it. So here we go. Today I decided to use pictures of Albert Einstein, which in retrospect perhaps wasn't a good idea. I'm used Albert Einstein because he was the one that initially proposed the idea of photons having a quantized amount of energy. So there we go. But he also wasn't a big fan of quantum physics, so maybe this is a little bit disrespectful. I didn't realise that today is Valentine's Day. That's how out of touch I am. So happy Valentine's Day to everyone, and what better way to spend Valentine's Day than doing physics with your friends. Here's a picture of Albert Einstein, the first person ever to have used the word LOL to troll his students, I think. I think that's what he's written on the whiteboard, the blackboard behind him. Anyway, let's go. The first thing we're going to do is some unit conversions. A lot of what we're going to do today is converting units of energy. In physics, when we look at particle physics and quantum physics on the very small scale, joules as a unit of energy isn't particularly useful. So we use a different unit. You don't have to know the details of this, but you are going to have to be able to convert it. Well, here's a picture of Albert Einstein as a very young child. Okay, so here are 8 questions. And in these 8 questions, you've got energies in either electron volts or mega electron volts, that million electron volts they are, or other units here. And what I would like you to convert those energies into. You will need a calculator, I suspect. And I'm going to give you a few moments just to rattle through all of these. And then we'll go one at a time, just chucking your answer into Spiral, and I'll give you a tick or a cross as appropriate. But I'm just going to give you a few moments now. I'll be quiet while you just work through doing some of these unit conversions. Let's put a timer up, shall we? Timers are good. Let's put a timer up for 4 minutes, I would say. See how many of these you can get done in 4 minutes. Once you know how to do them, it won't take you long to do each one. I've written the conversion factor at the top there to help you out. What I might do is edit all of this bit out of the video once the stream has finished. I'm not able to edit videos until 24 hours after the live stream, but as soon as I can, I'll probably cut all this bit out. No, you can't yet, Lex. It's because I haven't enabled the box yet. You can click the link and you can get ready, and then as soon as I hit go on my screen, you'll be able to type your answer. So you've got 2 minutes left. Anyone that's just joining us, we're working through these 8 unit conversions just to make sure we know what we're doing, because we're going to be doing that a lot today. And click the spiral link below. Just type your name. Doesn't really matter what name you type, just so you can give me your answers. Just less than a minute left. Oh, good morning, Global Carrot. I don't recognize the name, so it's good to see you. If you want to give answers to questions as we go through, please do click the spiral link and then be ready just to type your answers in. Okay, so that's the end of that. If you just type your answer for the first one, just the first one into spiral. Let's see what it looks like. Just waiting for a few more people just to type their answer in. Okay, so only 7 people are on spiral at the moment, which, okay, I mean, it's half term for a lot of people, so maybe they've decided that they want to give it a rest for a week, but never mind. I'm still here and you're still here, so that's good. I'm going to show the answers, but with the names hidden, and you won't know what the order of the names are, so it's still very, very much anonymous, but I am going to show the answers here, just so you can see what it looks like. Let's see if I can switch this across. Boom, there we go. So you can see this answer is great. This answer is a factor of 10. It's a power of 10 out. This answer is great. This answer is 2 powers of 10 out. This answer is great. This answer is great. More confidence. You can do it. Clearly you can do it. This answer here, the second one is correct. The first one is not. So the way that you did it, bounce that back over so that you can see the PowerPoint again. The way that you did it in this case is you multiplied the energy in electron volts by this factor. So 1 electron volt is this, which means about half electron volt is about half of this. So you multiply the 0.511 by this factor. That's how you convert that way around. Right, for number 2, type your answers in for number 2, please. Okay, so we've got a few answers here. It looks like a few of you have fallen into one of the dastardly little traps that I put in. So in this question, you'll notice that is mega electron volts. That's millions of electron volts. So you do have to keep an eye open for that sort of thing. So here are some answers. These are the ones that are marked as correct. Oh, that one's just come through as well. So that's correct as well. So the way you do this is it was 106 million. So 106 mega means 106 million. What I do... Oh, okay, Ansh, it's good to see you. Sorry, Pooja, it's good to see you. Do make sure you click that spiral link. Just notice your chat thing there. Do make sure you click that spiral link and then you can interact live with us. It's definitely worth doing. So you type, what I do is I type 106 and then I do the times 10 to the power of button on my calculator and then 6, rather than trying to convert it into standard form. There really is no point. If it says 106 mega electron volts, that's 106 times 10 to the power of 6. So that's what I put into my calculator. 106 E on my calculator, 6. And then, because we're converting into joules, I multiplied by 1.6 times 10 to the power of minus 19, and I got the answer that I've marked correct there. This answer here, I've marked it as correct, and perhaps I shouldn't have done, because the last digit is wrong. That's been incorrectly rounded, and in A-level, that would cost a mark. In GCSE level, you might just get away with it, maybe. A-level, you definitely won't. This one over here, a power of 10 error, so you didn't notice the mega, and that will cost you 1 mark. And I'm not sure what's happened with it. This is the answer to the previous one, I think. So we're now looking at question 3. I'm not going to do all of these. I just want to do a few to make sure you've got them, and then I'll just reel out the answers. So question 3, I'd like you to type your answer into Spiral now, please. I suppose I better work out the answer myself. I made these last night. So we want the answer in mega electron volts. Just a few more people are waiting for the answers to come in. Okay. If you don't have an answer, then to save me waiting, just let me know. Just drop a message in saying, no, I don't have an answer, and then I'll know to move on. So I don't want to move on if there are people typing an answer, but I also don't want to wait if people haven't managed to get there. Okay, so let's show, again, I'll hide the names, and we'll just show some answers here. So this is question 3 we're looking at. Question 3 was 2.16 times 10 to the negative 11 joules. And the answer, as you can see, is 135 mega electron volts. But let's go through how to do that. Let's just bounce back to the question. Let's see how to do that. In fact, what I'll do is I'll do it in writing. I'll do a worked solution because that might help. So we had 2 point, hopefully that's coming through clearly enough, 16 times 10 to the minus 11 joules. Now we know that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. We know that, that's given to us. That means that the number 1 is equal to 1 electron volt divided by 1.6 times 10 to the minus 19 joules. Okay? That's what it is. If this value here on the left is equivalent to the value on the right, anything you divide by itself is just the number 1. So this is just the number 1. And also, this is just the number 1 as well, of course. You could do it the other way around. And the reason why I'm writing this is so that I can do my unit conversions very carefully. I don't have to guess whether I times or divide by the by this factor here. Because I want joules to be got rid of, I want to cancel out the joules and have something in electron volts, actually mega electron volts, but we'll do that in a second. I need to multiply this by the number 1, which is written in such a way that the joules cancels. And that's this way here. If I were to multiply this number by 1, which is written as 1 electron volt divided by 1.6 times 10 to the minus 19 joules, then can you see that the joules is on the top of the fraction and on the bottom, so it cancels. So if I type into my calculator 2.16 times 10 to the power of minus 11, and I divide that by 1.6 times 10 to the power of minus 19, that gives me, in electron volts, 135 million. But that's in electron volts. Now I wanted mega electron volts. Mega means million. 1, 2, 3, 4, 5, 6. I'm moving the decimal place 6 times to make it a million. And there's the answer. So I was multiplying by this factor, which is the number 1. Question 4, which I'll just briefly flash up on the screen so you can see it. Question 4, I'll just go through the answer to this one. It was an amount of energy in joules converted into kilo electron volts. So let's go through that one here. The amount of energy, this is question 4, the amount of energy we had was 2.24 times 10 to the minus 11 joules. And we want to multiply that by the number 1, but in a way that means the joules cancels. So we know 1 electron volt is equivalent to 1.6 times 10 to the minus 19 electron volt. What am I doing? Joules. And that way I can cancel the joules. And I'm left with electron volts, which is the unit I want. So if I put that into my calculator, my 2.24 times 10 to the power of negative 11, the trick with this is to use that button on your calculator that has times 10 to the power of. Otherwise, you'll accidentally make mistakes with the order of operations. Your calculator won't understand what you've entered. Now, when you do that, you end up with 140 million electron volts. But for some perverse reason, I want it in kilo electron volts, which means kilo means 1,000. So I moved the decimal place 3 times. So this is 140,000 kilo electron volts. Ooh, okay, let's just tidy up my K there. Are you finding this helpful going through this? I'm not sure if this is beneficial or not. I'm just going through a few of them. I don't really want to go through all of them. Maybe we'll just do one of the other way around now. We'll have a look at question 5, because that's converting from kilo electron volts to joules, and then we'll call it a day on this task and we'll move on to the next. But I will just read out the answers. So question 5, we've got 494,000 kilo electron volts, which we want to convert into joules. Well, kilo is equivalent to 1,000, so I could write another 3 zeros in here if I was afraid of standard form, but that's fine. Now I want to cancel the unit electron volts and be left with the unit joules. So how do I do that? Well, I'm going to type in here 1.6 times 10 to the minus 19 joules is 1 electron volt. That's that definition we had before. That way I'll be able to cancel the electron volts. So what do you put into your calculator for answer for question 4 or 3? How can you put something you don't know? I don't understand the last part, but what I'll say, I'll tell you how to put this into your calculator. I'll tell you how to put question 4 into your calculator to start with. Let's pick that up. So I would type in 2.24, and then I'd press the button that has written on it something like, I don't know exactly what your button says on your calculator. Every calculator is different. Some of the most popular calculators in the United Kingdom use that button. My calculator just has a capital E on it. And then I would type in minus 11. Then I would type times. Oh, no, I wouldn't. I'd type divide because I want this on the bottom. So I'd type divide. And if I press that, it might turn this into a fraction, and that's okay. And then I'll do the same thing. So 1.6, and then the button is times 10 to the power of x. And then I'd type in the minus 19, and then on your calculators you just press the equals key. My calculator doesn't have an equals key, and that would give me the answer in electron volts. But if I want it in kilo electron volts, I would then divide the answer by 1,000, because kilo is 1,000, and that would give me my answer in kilo electron volts. Does that help, Ted? I'm not sure if I understood the second part of your question. How can you put something you don't know? Some calculators have a solver where you can put variables and it will solve for them, but it's better to rearrange the equations yourself. It really is. Yeah, okay, great. So what was the answer? I haven't actually worked out the answer to question 5 yet. Sorry. So 494,000,000. I'm just typing it in longhand. 1.6 E19 minus times. And you got... We wanted it in joules, didn't we? Yeah, so we got 7.904 times 10 to the... This is for question 5. 7.904 times 10 to the minus 11 joules. And I'll just give you the answers to the rest now, I think. I'll read out the sum as I'm doing it. So question 6 is 938 mega electron volts. By the way, that's the equivalent energy, the mass equivalent energy for a proton, I think, off the top of my head. So 938 E is mega, so E6. And then I'm going to multiply that by 1.6 E19. 1.6 E19 minus, 1.6 times 10 to the minus 19, and then it gives me my answer in joules of about 1.5008 times 10 to the minus 10 joules. Question 7 is 1.504 times 10 to the minus 10, and convert that into electron volts first. That's 1.6 E19 minus divide, but then I want it in mega electron volts, so I divide that by 1,000,000. And that gives me 940 mega electron volts. So question 7 is about the same, the mass equivalent energy for a neutron. It's a little bit more massive. And if you watch the videos about particle physics, then you'll understand that because the neutron's a little bit more massive, it's a little bit less stable. And question 8, 1.9712 E10 minus, so that's in joules. I'm going to divide that by 1.6 E19 minus to get the number of electron volts, which is loads. I've got to count the digits now. 1,232,000,000 electron volts. Is that right, or I made a terrible mistake somewhere? It's far too many, but there we go. Yeah, I think that's right. I want it in kilo electron volts. That gives me 1,232,000 kilo electron volts. So that's those unit conversions. That was a good little warm-up exercise. We're now going to move on to the real stuff. The real stuff. For 8, you got that. Yeah, that seems right to me. That's good, Pranav. That's what I got. Is that not what I read out? Thought that's what I'd read out. I might have read it out wrong. But yeah, that's what I got. I agree with that. So question, so this question here, I'm going to just give you the answer to this because it's a bit more grunt work with a calculator and we're pushed for time a bit, so we'll move on. But this here is an energy level diagram. Now in GCSE level, you will learn about something called the Bohr model of the atom. The Bohr model of the atom says that electrons... Did I? Oh, my apologies. I may have sounded confused. I didn't feel confused, but I'm sorry. It certainly sounded confused. Yes, the Bohr model of the atom is the one that you learn about at GCSE level, where electrons occupy shells, and you can fill up those shells. And you can start with 2 electrons in the first shell, then you can put 8 electrons in the next shell, and then depending on who teaches you, they might say either 8 or 10 or 16 or some number of electrons in the next shell, and every student scratches their head and wonders why teachers are telling them different things. And we'll come to that. We'll come to that today. So for hydrogen, we're going to focus on hydrogen. These shells... well, all atoms, the shells have certain energies. They're all negative. And what that means is that if I take an electron and I stick it into the atom, it loses energy as it gets bound to the atom. It releases energy when it gets bound to the atom, which is why these energies are negative. And if you want to get the electron back out of the atom, you have to put energy in to get that electron back up to 0 energy and get it out of the atom. So all these energies are negative. And for hydrogen, the energies for each of these shells, according to the Bohr model, is this. It's 13.6 electron volts divided by n squared, or minus it, because all the energies are negative. Now, the n squared, n refers to the energy level, where the first energy level is labelled 1, the next one's labelled 2, and so on. Now, that's fine, but that's not the best model we've got. And so at A-level, particularly if you do chemistry, you'll learn about things called subshells. But first of all, before we move on to subshells, let's just do the calculation. Let's get the energies of each of these, what we call energy levels. And here they are. The energy for each of these energy levels. And you can see they roughly correspond. So 13.6 is there. That makes sense. Minus 13.6. And minus 3.4 is about here. Minus 1.51 is about here, and so on. And I'm only going to use the first 4 energy levels in everything we're doing today, because we don't want to go too complicated. So if I ask you, how many electrons can you put in the first energy level? I've kind of already given you the answer to that. But go ahead and just pop it into the chat. Let's not bother with spiral for something like this. How many electrons do I stick in n equals 1? I imagine most of you will know this. You take an atom and start filling it from the middle. How many electrons can you put in that first shell? Yeah, 2. Of course you can. But do you know why? Why 2? It seems like a weird number. Why 2? Yeah, exactly. No one's quite sure why. But listen, I can tell you why. It's because electrons are fermions. Now, I recorded a whole 12-part series on particle physics. And in that series, I talked about fermions. And the main property of fermions is that you can't put 2 fermions with the same quantum numbers into the same state. Well, they can't have the same quantum numbers. So as Pranav says there, they're fermions. They can't be in the same quantum state. And the quantum number that's different for those 2 electrons is their spin. One spins up, one spins down. So spin is a quantum number that can have 2 values, up or down. Positive a half, negative a half. The half spin because it's a fermion, but we don't need to go into that now. There are 2 spin states, and they have different quantum numbers. So the quantum numbers that the electrons have down here is n equals 1, s equals either plus a half or minus a half. And those are the 2 possible states here. But if we move on to the second energy level, how many electrons can you put in that second energy level? I know this is hydrogen, so you're going to say, well, you can't get that many electrons in hydrogen. But let's imagine we can. We can get the whole thing really cold, and somehow we can get it really supercharged hydrogen. I don't know how you could do that. But for any atom, we're putting electrons into n equals 2. How many electrons can you get in n equals 2? What's the maximum number? 8, of course it is. And this is something we learn at GCSE level. 2, 8. So why is it 8? Any idea? Why is it 8? I should have put pictures of Niels Bohr in here. All I'm doing is about the Bohr model of the atom. I shouldn't have used Einstein. Any idea? Why is it 8? I'll give you a clue. This energy here, this is what we call the S shell, the spherical shell, still has just 2 electrons in it. But both of these are the same energy level, so they're both... Yep, there we go, Pranav, you've got it. So both of these are the same energy level. So they've both got the same n value, n equals 2. We can get 2 electrons in here, therefore we can get 6 electrons into here. And this is the weird bit. This is the bit that's a bit difficult to get your head around until you learn about how the quantum numbers work together. There's another quantum number which we're labeling L. Okay. I'll tell you, L is the orbital angular momentum quantum number. And it's also a quantum number. So you can have 2 electrons with the same energy level, the same spin, as long as they have different angular momentum quantum numbers. Whatever that means. And it's part of this long wave equation called the Schrödinger equation. You can plug various wave functions in and get solutions. And there are certain numbers in those solutions. And as long as those numbers are all different, it's fine. So it turns out that L can take a value as long as it's less than n. You can have any value of L as long as it's less than n. So n equals 1, you can only have L equals 0. But n equals... Oh, it can't be negative. N equals 2, you can have L equals 0, and you can have L equals 1. N equals 3, you can have L equals 0, 1, or 2. N equals 4, you can have L equals 1, 2, 3, 0, 1, 2, or 3. So you can have those. And each time you go up, you can put all of these, you can put the same number, 6 electrons in these. 6 electrons in these. In the L equals 2, you can put an extra 4 electrons into each of those. So you can get 6 electrons into your P, that's what we label it, your P subshell, which is angular momentum quantum number equal to 1, L equals 1. When L equals 2, you can put 10. So 6 electrons in here, 10 electrons in these. So you can have, for n equals 3, you can have 2 in this shell, 6 in this shell, 10 in this shell. And so 2 plus 6 plus 10 is 18. Because they've all got different quantum numbers. So there's obviously a quantum number missing here then, isn't there? Because why can I have 6 here with the same value of L and the same value of N if there are only 2 spin states? And the answer is that there's another quantum number which is called the magnetic quantum number. It's sort of not an orbital angular momentum, it's an electron angular momentum quantum number. And it can have any value between minus L and L. So when L equals 0, it's only 0, it only has one number. When L equals 1, it can go from minus 1 to 0 to 1. And you can have 2 electrons in each of those because you've got 2 spins. So 2 electrons in in -1, 2 electrons in 0, 2 electrons in +1. That's 6 electrons in total, and that's why when L equals 1, you can get 6 electrons in those shells, in those subshells. But for D, where L equals 2, you can go -2, -1, 0, 1, 2. So that's 5 multiplied by 2 for the 2 spin states. Yes, they do. They absolutely do repel. Yep, they repel each other, and that's why for hydrogen, for example, this just you wouldn't be able to get as many electrons in. But if you've got an atom with a nucleus with much more positive charge, then the attraction would be greater than the electron repulsion until you've got enough charge in there. And then you end up with something called charge screening, but I'm not going to go into that right now. So filling up these atoms from the bottom, actually it turns out that the energy levels do split a little bit. So we've drawn n equals 3 here, all on exactly the same energy. That's not quite the way it is. As you put electrons in here, they interact with each other and change the energy of those energy levels. And you can detect, a classic example is sodium. If you get sodium and you excite it so it glows, you can see the yellow light that's emitted from sodium actually is two very, very closely related colours. And the reason why they're slightly different is because of the two subshells having slightly different energies. So that leads me nicely on to what I want to spend most, I say most, I've only got 23 minutes left, but some of today talking about, which is emitting photons, absorbing photons, or emitting energy, absorbing energy from atoms. So there's a concept here called excitation energy. And the excitation energy is the difference in energy between two energy levels. You can only emit photons with an energy equal to an excitation energy. You can't emit photons from an atom with energies not equal to an excitation energy. It's in quantum physics. That's why there's certain values. Quantum means quantized, means certain values. That's why there are certain values of energy that these electrons can take. These photons can take. These photons can only take certain values of energy because there are only certain excitation energies within your atom. We can also only ever absorb a photon if it has exactly the same amount of energy as the excitation energy in an atom. If it doesn't have that amount of energy, then it cannot be absorbed. The photon goes straight through the atom unabsorbed. So we've now got the concept of photon energy. You know, photons are these particles. Are they particles? I'm not going to get into that now. Let's call them particles that carry this electromagnetic energy. And we know that electromagnetic radiation can be described with wave equations. So to link those two ideas together, this is Einstein's big revelation here, we've got the photon energy is proportional to the frequency of the electromagnetic radiation. You're going to want to write these down because we're going to be using these in the very next slide. In the very next slide, we're going to calculate the energy. They are subatomic, absolutely. 𝗟𝗲𝗲, we are talking about subatomic particles. Quantum physics is going on within the atom. This is weird world of physics where a photon could pass straight through an atom as though it wasn't there because it doesn't happen to have an energy equal to the excitation energy. So we're going to need to be able to calculate the energy of a photon if we know the frequency of the electromagnetic radiation and vice versa. Planck's constant here is h. It's one of those numbers that's really handy to remember in physics. Speed of light is here. I know it's not quite that. Speed of light does have an absolute value, but we're going to go with this because that's what we use at GCSE and at A-level, so it'll be okay. 3 significant figure, speed of light, 3 significant figure, Planck's constant. So you've got those down. Your questions then. Here they are. I would like to know the energy of the photons in these, I've called them electromagnetic radiations because I couldn't think how better to word it. Electromagnetic radiation of that frequency what is the energy in electron volts? I'm doing that horrible thing as well, for the photons in that radiation, and so on. Now, I'm going to give you about 3 minutes, I would say, to try to work through as many of these as you can before we go through the answers. And if you could put all of your answers together into spiral at the same time. So let's get the timer loaded. Where's my clock gone? There it is. 3 minutes. So get working on those. As soon as you've got the answers, I want you to go ahead and pop them into spiral. You can do it as you go along if you want, but see how many answers you can get. In case you've forgotten, nano, which is the lowercase n, means 10 to the minus 9. You've got less than a minute left. As soon as you've got them, you can chuck the answers into spiral. If you are just joining us and you're thinking, why does he keep talking about spiral? There's the link to it. Click there, type any name you want, and then you'll be able to give me feedback. Okay, time's up. So pop your answer into spiral, whether you're finished or not. Let's see what you came up with. In fact, let's switch it across so we can see the answers as they start to appear. Doesn't matter if you're done or not. Remember, your names will be hidden, so it doesn't matter. This is good. First three are correct there. Anyone else? Yep, it's good. Yeah, it's good. It's the first two. Yeah, so not too sure. E equals 2.17. Could not get past that. Okay, so I'll just go through question 1 and 2 as worked solutions. Yeah, you're a bit stuck. That's okay. I'll go through question 1 and 2 as worked solutions. Let's just scroll up, give myself a bit of blank space. So question 1, we had the frequency of the electromagnetic radiation was 3.28 times 10 to the 15 hertz. And we want to find out the energy of the photons. So the first thing we need to do is multiply that by the Planck's constant to get the energy. So the energy of the photons, which is HF, therefore 6.63 times 10 to the minus 34 joule seconds multiplied by 3.28 times 10 to the 15 hertz gives us, and I'll get my calculator, 6.63 E34 minus enter 3.28 E15 times. Okay, so this is where you sort of got to the 2.17. I'm going to include a few more digits here as guard digits in case any rounding errors crop up. Oops, minus 18 joules. Now I now need to turn that into electron volts. So I remember how I do my unit conversions. This minus 18 joules, I want to multiply by the number 1 so I can cancel the joules and be left with electron volts. And on the top of the slide, it said that 1 electron volt was equivalent to 1.6 times 10 to the minus 19 joules. So I'm dividing by the charge on the electron, 1.6 times 10 to the minus 19. And that gives me 13.59. So let's round it to 13.6 electron volts. So that's question 1. Let's just have a look at question 2. Just the second one, and then we'll move on to the next part. So question 2, we've got a wavelength this time, which is in nanometers, 122 nanometers. So that's the same as 1.22 times 10 to the minus 7. Actually, I won't do that conversion because that might confuse. I'll just do 122 times 10 to the minus 9 meters. I need to find the photon frequency before I can work out the photon energy. So I use the wave equation. The speed of light divided by that, so 3 times 10 to the power of 8. 3 times 10 to the power of 8 divided, scroll down a bit, divided by the wavelength, which is 122 times 10 to the minus 9, is going to give me the frequency, which is 2.459 times 10 to the power of 15 hertz-ish. Now I've got the frequency, I can multiply that by Planck's constant. So this is to get the frequency, this is to get the energy, but it will be in joules. So that's going to be, I've written a 4 there. 6.63 times 10 to the minus 34 multiplied by the frequency, 59 times 10 to the 15, and that will give me the energy in joules, 6.63 E34 minus times, and that's not a lot of joules, 1.630 times 10 to the minus 18 joules. But I want the answer in electron volts, so now what I do is I write it out. Let's write it out full because this is the bit that's confusing some people. That's joules. I keep the unit there. I multiply that by. I want to cancel the joules and be left with electron volts. I know that 1 electron volt is 1.6 times 10 to the minus 19 joules. That will allow me to cancel the joules. And I'm left with 10.2-ish when I round it. 10.2 electron volts. So there's the first two, and the rest of them you follow the same approach, the same pattern. Just going through the answers. Here they are, and there's the rest of them. Okay, so the next question is, can the following photons be emitted from hydrogen? So here are some photon energies. Here's some different photon energies. Well, some of them might be the same, some of them might not be. Some of them can be emitted from hydrogen. In other words, there is an excitation energy equal to this. Some of them cannot possibly be emitted from hydrogen. What I want to know is which ones can and which ones cannot. And you can give your answer as just a string of yes, no, yes, yes, no, no, yes. You know, that's okay as long as they're in the right order. And pop your answer into spiral when you've got it. I'm going to give you a bit of time for this one. I'm going to give you about 3, maybe 4 minutes, because the easiest way to figure that out is to calculate the excitation energies. That's the difference in energies that are possible. Then it's much easier to have a look. That's sort of 8 1, 2, 3, 4, 5, 6. That's 6 calculations, but they're only simple subtractions. So I think 3 minutes is okay for that. Where's my clock gone? There it is. You don't have to wait for the timer to finish. If you manage to do it quicker, brilliant. I'll show your answer quicker. So I just had a message come through saying not sure how to work it out. And that's okay. So the difference in energy levels is the excitation energy. There are 6 possible differences in energy levels here. There's when you move from n equals 1 to n equals 2, from n equals 1 to n equals 3. Sorry, we're talking about photons being emitted. So when you move from n equals 4 to 1, or from 3 to 1, or from 2 to 1, or from 4 to 2, or from 4 to 3, or from, what have I missed? 3 to 2. So there's the 6 different possible excitation energies. You calculate an excitation energy by taking the difference between these 2 energy levels. And if these correspond to those differences, then it's possible. And if they don't, then it's not. So some of you have done really well. A few of you have got 1 or 2 wrong. But other than that, some of you have done really, really well on that. So let's just go through the answers quite quickly. Let's get rid of the timer. The first one, is that possible? Absolutely yes. Absolutely yes, that is possible. So 0.66 electron volts. Let's work out where that's possible. Yeah, if you were in n equals 4 and you drop to n equals 3, so an electron drops from up here to the next one down, it will emit a photon of that energy. So that's possible. The difference between n equals 4 and n equals 3 is 0.66. So then we look at the next one. Is that possible? 2.55. The answer is yes, it is possible. But can you work out why? N equals 4 to n equals 2. If you drop from n equals 4 to n equals 2, the difference between those two energies is 2.55. So perfectly possible. The next one, no. Sorry, there's no energy difference corresponding to that. That is the energy level n equals 2. And there's no 6.8. And there's no 0. If an electron was sort of fell into the atom and landed on n equals 2 from originally having no energy whatsoever, I suppose that would be possible, but that would only be if the electron was unbound initially and just unbound. So no, that's not possible. And next one, 10.2, that's from n equals 2 to n equals 1. The next one, no, none of these transitions correspond to that energy. That's not possible. I said that one right. 10.2. I think I might have said that one wrong. 10.2 on top of 13.6. No, I was right from that one to that one. And the last one as well, yes, it is. It is possible, but you're going from right up here down to there. So 13.6. Yeah, from n equals 3 to n equals 1. The last one is possible. That's the difference in energy level. So right, you've worked out if the photon's 2 to 1. Yeah, that one is 2 to 1. That one is 3 to 1. Yeah, that's right, Jack. And so the next bit here is working out whether photons can cause hydrogen to become excited. Now, with 3 minutes left, we don't really have enough time to... We never have enough time. I don't think we really have enough time to go into that. The process for this would be, is the energy corresponding to this photon equivalent to one of these excitation energies? But unlike before we were emitting photons, this time we're absorbing photons. But it doesn't matter. It's exactly the same approach. Is this photon energy, or does this photon energy correspond to one of those transitions between two energy levels, what we call an excitation energy? So we'd have to convert each of these into electron volts, first of all. Now, long story short, you've actually already converted all of these into electron volts, I think. I just used the same numbers again, but there's the answers to them. With 3 minutes left, we're not going to get a chance to do that. But it's the same thing as you did last time. The last two skills, converting from wavelengths and frequencies into energies in electron volts. Then the skill you've just learnt, which is looking at that energy and seeing if it corresponds to an excitation energy, we're just putting those two skills together. So the next idea is what happens with incident electrons. With photons, all of the photon is absorbed, or the photon passes straight through the atom without interacting with it. With electrons, incident electrons bombarding, striking, colliding with an atom, that's not quite the case. Because the electron that bombards the atom doesn't get absorbed, it just gifts energy to the atom, making it excited by having an electron in that atom go to a higher energy level. But only if the kinetic energy of the incoming electron is higher than or equal to one of those excitation energies. And if it's not, then the electron that comes in goes straight through the atom. That's weird. That's not classical. That's weird physics there. Electron going straight through the atom if its kinetic energy is below an excitation energy. But that's what we observe. So the next part here, you have these energies of electrons. If you've already worked out the excitation energies, this is a little bit more trivial. You can see all these energies. You just say, right, is there a transition equal to that particular energy? So 12.5 electron volts. Well, no, there's none equal to exactly that energy, but it's more than the transition from n equals 2 to n equals 3, for example, or more than the transition from n equals 2 to n equals 4, or, it's more than that transition. So we can cause, for example, from n equals 2 to n equals 3, we can cause excitation. We can cause a bound electron to get excited. Of course we can. From n equals 1, we could go for, sorry, I'm reading this wrong. From n equals 1, we can go to n equals 2, or we can go to n equals 3. I prepared this last night, forgot what I'd prepared. So if you are on n equals 1, can you excite with that kinetic energy electron? Yes, you can either go to n equals 2, or you can go to n equals 3. Right, next one. If you're on n equals 2, can you excite with this? No. No, you can't. If you're on n equals 3, can you excite with this? Well, yes. We can go to n equals 4. And notice I'm just giving you the answers because we really are pushed for time. Wish I could go on for 2 hours, but I'm not allowed. I'll get told off. Electron volts. Okay, so if we're on n equals 2 and we have an electron coming in with this kinetic energy, can it cause excitation? Yeah, of course it can. It can go to n equals 3. How about if we're on n equals 1 and we have this electron? No. Look, the next one up is more than 10 electron volts. That's just, that electron's going to pass straight through that atom. And last we're on n equals 1. Can this cause excitation? Technically, no. Although it looks like, well, it's got more energy. Why not? The electron would be liberated from the atom. The bound electron would no longer be bound. That's not excitation. That's something we call ionization. All right, it's a shame I had to rush those last few slides. I always do. It's a real problem. But it's because we spent a bit of time going through some of those work solutions, and I think that was worth doing. Maybe I'm wrong. You know, drop a comment below if you think that was worth doing. If you think, no, just rattle through it, then let me know. I'm here to help you. The key thing about quantum physics that makes it so weird is that, unlike classical physics, where particles will collide with each other and you'll have a definite outcome, with particle physics, I've said, oh, that electron will go straight through, not without interacting. But actually, that's also possible for electrons in case number 1, 3, and 4, and even 6. You could have an electron incident on an atom that passes straight through. It's just about, oh, okay, bye, Jackson. It's just about probability. Whether or not the particles can interact. A very, very different type of physics to what you're used to. But this is what's observed, and it's why we get things like quantum tunneling, which is responsible for how the microchips inside your mobile phones work and things. Very, very exciting. So next session, we're going to be looking at things like the photoelectric effect. Can't remember exactly what else is going to be in that, but definitely the photoelectric effect will be in that under the quantum phenomenon session. And if you've got any questions, do ask them. Maybe drop them in the comments below or something. I can respond to them. If you haven't yet subscribed, then do, if you like it. You might find that there's other videos come online. I do tend to record quite a few videos at the moment as well. I'm enjoying that. My next video I'm recording is the next one in my astrophysics, my astronomy program. But there we are. We're done. So thank you very much. Thank you for your patience. Thank you for tuning in on a Sunday, a Valentine's Day, but it's a Sunday during what's now half term for most people. So that's commitment. Congratulations. I'm impressed. I do hope you found it useful. Thank you very much for tuning in. Stay safe. I'll see you next week.